All right, students. On Thursday, when you come to class, I won't be here. I'll have either a video lecture or Stephanie, my student teacher, will do the stars, the reader goals, and the movie goals. If you want, you can come to third period class tomorrow, and I'll have a little chunk of time where I can help with your solar house model. And I'm guessing Stephanie might be willing to help you with that Thursday second period, but I don't want to commit her to that until she and I have a chance to talk. This all just came together this morning. So if you want help with your solar house plans, you could bring them tomorrow, and in part of our period, we'll have a little bit of time. Are there any questions about the rest of this unit? Block day is for the final ramp up to the exam. Friday is the exam. Monday, you turn in your solar house plans, and Tuesday, we start Unit 8. Remember, the water bills are due in the next unit. Question, viewer. Yeah, bro?
Are we going to review still on Thursday if you're not here?
Yeah, so you would either have Stephanie leading the review, or I'll videotape my lecture. I haven't checked with her. She doesn't have to teach period 2. She often makes other plans. We haven't talked. It's whatever works for her. Anybody else? Yeah.
If you want to come in here during seminar tomorrow, like, are you going to be really thinking about having this session? So before you just write the past,
You're whispering. I didn't hear that last one.
like the buildings, do you need that, or just like any past?
Let me think about that. The admin sent an email literally last week that says, please remember to use the golden pads and not let kids go to the library, and like super strict. She was really, one of our administrators was very, very focused and serious about that. There's got to be a way around the golden ticket thing, but yeah, just make sure that your teacher note has their phone extension on it. So I'll verify with them via the phone, like, hey, Kai's here, she's going back now, so that we have like phone contact, and then it's fine. Everybody else understand what I just told her? Yeah? Phone contact? If you want to come during the seminar? All right. Let's finish nuclear today. I think we can do that. You're going to need possibly 3 separate papers. Your 7.4 you'll need for sure. Your nuclear reaction paper, you'll need maybe this one. And your nuclear power plant notes you will need. I don't know how many papers that is. You need reaction, reactor, and 7.4.
It's weird. It's sitting in the back.
Good.
So far away. Yeah.
I want to get you a little black box with 2 little holes.
Did I do that?
Yeah, that's sweet. You never have to look like you're
We can get like
little cardboard
bands
box.
and wires. We'll ship that up.
Yeah. Into the
Physics
go outside.
Yeah.
Um, my students and many students nationwide are outraged by how much detail they have to know about the nuclear energy stuff. A few things of the reaction, the 235 in particular, the neutron in particular, the 236 in particular, like explicitly and exactly that part. Like you have to like perfectly nail exactly letter for letter, number for number, word for word this part. You don't really have to know which radioactive decay products, but it might be important that you do. Heavy tin, heavy molybdenum. Some reactors make barium and krypton. You know, different chemistry because of different design. But the reaction you have got to know explicitly and exactly, and no other way of saying it. 235 plus neutron makes 236, which gives off decay products, neutrons, and energy. The heat, I'm sure everybody can remember. The neutrons are going to be tough to forget. So you could either memorize the average ones, the other common ones, or just call it radioactive decay products. Conceptually, different sciencey people use different words. They call them the heavy radioisotopes of spent fuel, or like 1,000 other ways of saying that I don't know. When I told my dad, my dad's a nuclear physicist, when I told my dad radioactive decay products, he was like, yeah, I guess, but they don't, that's not what he used in his career. My dad worked at a nuclear power plant. Did I tell you all that on it? Like, you know? Back in the day. Did someone raise a hand when I was looking at those, by the way? Ah. So that's the beginning of number 36. Then in number 36, you have to also describe a reactor. So let's see. Check your notes. I'm guessing everybody had the reaction by now, right? Please God. Okay. And then for the reactor, 3 cycles. Oh, someplace in your notes, you probably want to have the words heat exchange system. Like when you bring a cold water into the steamy hot sauna, heat goes from the air to the water inside the bottle. Heat exchange system. Each of these cycles, please look up, primary exchanges heat with secondary, exchanges heat with tertiary. In those transfers, things happen. Like the coolant goes past the fuel rods to make hotter coolant. That hot pipe turns cold water into steam. That steam becomes cold water because the tertiary cycle condenses the steam down to cold, taking heat out to the environment, either the air or the ocean. Or the river, I guess.
Can you say that slower?
Sure. Primary cycle. Do you understand what I mean by the heat exchange system, the primary cycle? Where you've got some hot rods, that part, you know, the heat of the decay is heating up the coolant, right? So there's a heat transfer from the rods to the coolant solution. That makes the water hot in the primary cycle. Yeah? That would stay really, really hot and melt down if you weren't shedding the heat somewhere, but you are, please look up. You're shedding that heat to the steam generator. You're turning cold water into steam here. That's a heat transfer. The water stays in the pipe. It's not a water transfer, it's a heat transfer between 2 separate bodies of water through the pipe. Right? So you make steam. That steam would stay steamy if you didn't have a way to condense it back down into fluid liquid water. And so there's another heat transfer coming up. Please look up. Cold water comes in from the environment, and that cold pipe, just like your cold bottle in the sauna, takes away heat from the steam so that the steam becomes cold water and can be. So those are the three cycles. Each of them is a heat exchanger. You transfer heat from the rods to the coolant, from the coolant to the steam, from the steam to the environment. The heat exchange systems, that concept, you gotta have heat exchange somewhere, because it's not water exchange. A lot of my kids are like, water goes across the reactor and comes out of the tower. No, it's not water from the environment to the environment. It's heat to the environment. The radioactive stuff stays locked in pretty tight. And the steam generation actually stays in that loop more or less. Yeah?
What does it say? It says something used by the loop.
What?
Like, on the right side of your picture, condenser.
Condenser loop. So, some other vocab that I'm guessing you know. The pressurized water reactor is part of the primary cycle. That's radioactive. You gotta know all those words. In there, you've got the fuel rod assembly, which is fuel rods, which are stacks of pellets, which are made of uranium fuel. Gotta know that. The rate of chain reaction is moderated by control rods, which are usually boron. They're something that absorbs neutrons. Here's something I haven't told you that you'll need to write down because it's vocab that we just haven't said yet. In the United States, our coolant is water, 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 light water. As opposed to other parts of the world, use a very expensive liquid called deuterium.
You had this down yesterday.
What?
You had this down yesterday.
Somebody pointed out that I was fumbling my language. It's not deuterium, it's deuterium. Which is this, H22O. So here's the part where you take notes. There are two different coolants, light water or heavy water. In the US, we use light water. And light water is everything that you previously knew as water. Rainwater, rivers, lakes, tap water. Drinking water is light water, H2O. Two plain hydrogens and an oxygen is light water. And that's what we use in the United States. That is the coolant. That's what takes the heat away from the rods. Coolant. Stephanie? This here?
It's a nice hydro flask.
You want it?
I did.
Some parts of the world, though, they have fancy water. It's very expensive. But it lets you use crappier fuel. It's called heavy water. Before you do anything else, just keep looking at it. It's hydrogen with a neutron attached. Instead of hydrogen that weighs 1 atomic mass unit, it's H2. Hydrogen with a neutron, it's heavier. It's heavy hydrogen. So it's H2O. That's heavy water. Deuterium. Now,
Does it allow you to use crappy fuel?
all right. I can explain this now, but I think some people might get confused, and so I'm a little nervous. And I might fumble it, but I'll try. Y'all want to see why it helps you use crappier fuel? Yeah. If you're likely to get confused, I don't think you need to know it for the AP test, so you could just earmuff, but it might be a good way to exercise what you already know. The number of neutrons that come out of one reaction has to be sufficient to hit other 235s to keep the chain reaction going. The goal of any power plant is that those neutrons keep hitting other 235 at a slow controlled rate so that once you heat it up, it stays hot. Yes? Hydrogen can absorb neutrons, so if your coolant is plain water, you need pretty high concentrations of 235. If not, your water's going to take up hydrogens and all of a sudden your reaction will go cold. But if your water is already neutron saturated, correct? Then you'll have more neutrons remaining in the system, so you could use a lower quality fuel.
Wouldn't that also be more dangerous?
Well, your chances of a meltdown are less because in the absence of human intervention, you don't take off quite as quickly because most of these neutrons don't find more uranium. The ramp up of the reaction is slower if your 235 concentration is lower. Right?
Yeah, but there's just no, like the water's also absorbing neutrons sometimes in like when we use normal, it definitely not.
Yes. When we use normal water, light water is itself a moderator. So you need a higher concentration of 235 because there's not as many neutrons around because they're going into the water. Does that answer your question? How many of you actually know what I mean by this is a moderator, so you need a higher concentration of fuel around? Cool. If you don't know that, you don't have to. What you do need to know is that there are different reactor designs. In some countries they use one, in some countries they use another. You must know light water, heavy water. Heavy water is more expensive, but it lets you use crappier fuel. Second, first,
So which one's better?
I don't know how to answer that. I think it depends. There's probably some economy of scale. I heard on the Google machine that countries which use this can use crappier fuel, so they don't have to be supervised by the international community because they're not enriching. You see, Iran got in trouble because they claimed that they just wanted to do this and we're all freaked out they wanted to do that. But if they had this, they could get away with that and nobody would look twice. Right. So Canada uses deuterium heavy water reactors, and we're not worried about their enrichment goals because they're not enriching, they're using oil. No? Oh yeah.
Can you drink the heavy water? Like, is it just normal ass water?
I don't know.
Does it look like water?
Um,
Like, does it just look like normal water? Or is it weird?
It's important to point out that all isotopes are just isotope of an element which is chemically the same. So the only reason that you might not be able to is I'm not sure what the process of hydrogen decay does to your body. Hydrogen might sooner or later shed that extra neutron.
Yeah.
And when atoms shed neutrons when they decay, energy's given off, that's the scary part of the radioactivity, not the neutron itself. Neutrons are basically irrelevant. But the energy shift, when they lose weight, that could be the problem. So I don't know if it's bad for you.
Yeah, it's not radioactive, so you can drink it.
Okay.
Like the ice cubes sink instead of float.
Oh, cool. Yeah. That makes sense because they're heavier. Anybody else?
Actually, it says you have to drink a lot, like a few liters of it to kill you, because it has different chemical reactions in the cells, but a little bit won't kill you.
What are the different chemical reactions in a cell?
Performs, it's a little bit different in chemical reactions.
Which chemical reaction?
It's, I don't know. This is just, it's the first thing that comes up on
I wonder if it's the polarity issue.
Maybe. If your cells go
Neutrons don't have a charge, but the weight might affect the way that they organize.
Did you get that part I just said? Your cells might go bipolar.
Primary cycle, fuel rods, moderator, boron, light water, heavy water, two different designs because you have to cool it. Light water is water, water, heavy water is deuterium. Keep in mind also that in the secondary cycle, you make steam that becomes water, that becomes steam, that becomes water, that becomes steam, that becomes water. That's not chemistry, that's just temperature flux. You all know that steam becomes water, becomes steam, becomes water, because that, like, you know, comes, so, like, you got the song in, like, kindergarten. So there's nothing fancy about steam to water to steam to water. If you understand that you're adding heat to make it steam, and then you're taking away heat to make it water. And this part, the turbine generator electricity, that's like every power plant anywhere, not a big deal. Nothing fancy at that point. The only function of these is to shed the heat from the condenser loop, which is the third cycle. Cold water in, hot water out. I think I'm done with number 36 unless somebody had a question. Now, if we could stay in your study guide, I'll zip right on through a couple of these study goals. 37 says, make sure you understand what radioactive decay is. There's a few buzzwords you should know. Radioactive decay is when atoms fall apart, when they shed subatomic particles, when the heavy ones lose weight, isotopes dropping pieces, and something that I've never really told you, but now is time for you to write down. The loss of a neutron also gives off energy. There's a lot of fancy geometry to how that works. I'm not going to go any deeper into that concept because I don't understand it. But when atoms fall apart and they shed a neutron, there's a little burst of energy that comes out. And that energy can have interesting effects on chemistry or surrounding it. So the decay is the loss of the neutron, and the radioactive is the burst of energy that's released when you lost the neutron. And I thought it was interesting. I found out that my wife has radioactive, she's going to have a radioactive isotope injected into her bloodstream tomorrow. To mark which cells in her body are growing most quickly, so that they can identify where she has cancer in a special photograph that will show which cells are absorbing that isotope most quickly. They need more raw ingredients. You know, it's like if you're building a bunch of houses on that block, all the construction trucks are going to go to that block. They're doing all the growing, so they need all the materials. Where she has cancer, the cells are growing the fastest. So they inject her with a radioisotope that decays very quickly. Then like a specific, like 13 hours later or whatever, they use an X-ray which makes all of that radioisotope lose its neutrons and it shows up better on an X-ray film. So she'll have an X-ray which shows nothing except a few little cells, and those are the ones that soaked up raw ingredients the most. so they can map where she has cancer cells. It's neat, right? Radioisotopes. Knowledge. Number 38, the nuclear fuel cycle is like complicated and stuff. You start with ore, you enrich by getting rid of some baloney to make fuel, like that. And then, there's a lot of details that we haven't talked about because I don't understand them and you probably don't need to know them. Please look up. When the 236 splits, there's like a decay process for each of those products. They lose weight and then they lose weight and then they lose weight and they shed electrons and protons and neutrons, as a matter of fact.
Is that the dangerous part?
Yes, and like Homeboy like here says, they are the most dangerous thing in this whole entire equation is what happens to this stuff. That's all part of the radioactive decay chain or the nuclear fuel cycle. That was number 38. Number 39, does everybody understand why radioactivity is bad for you? Like why we care about health? How does this affect your body?
Gamma radiation inhibits the cell checkpoint, so it can produce space-induced kind of. So it
Kinda?
goes,
Yeah?
It can also cause cancer.
Kinda? And what does that mean? How does any of this come together? Does everybody realize that we are just chemistry? Like everything that you're doing is chemistry, like me making noises and moving is all just chemistry? So we rely on chemical reactions to run around and kick our sisters and vote Republican. And all of those chemical reactions can be interrupted by extra electrons or not enough electrons or this bond or that bond. So, back please. If anything messes up your chemistry, it might mess you up. So here it comes. Radioactive decay gives off energy. That energy affects bonds. Those bonds mostly don't matter because most of your chemistry is not that important, no offense. If one of your skin cells gets broken, chemistry stops working, most of the time, that skin cell just falls off or gets cannibalized and used for other stuff in your body. Almost every single chemical failure in your body doesn't matter. But 1 in a trillion of those chemical failures might affect DNA, which just happens to be important for regulating growth. And unregulated cell growth is cancer. Most of that cancer is irrelevant because unregulated cell growth might just make extra cells and that doesn't matter either. If you just have extra bone on top of your bone, you just got a thick bone spot, no big deal. And if you get extra skin cells, you know, it's like a skin tag. Anybody have skin tags? Usually they're in our armpits or near our armpits. Okay. Or a mole. Everybody has moles, just extra melanin stuff. Okay, who cares? But 1 in a trillion of those uncontrolled cell growth might affect the function of your body, and that's what we call a malignant tumor, a bad cancer. That can really mess with you. So it's a game of odds. First, that the radiation will mess up your chemistry. Second, that the chemistry will matter. Third, that it'll cause cancer. Fourth, that the cancer will be severe enough, so it's like a trillion, 1 in a trillion, 1 in a trillion, 1 in a trillion, where it actually causes harm to your bodily functions. More radiation exposure means you've taken more chances, and sooner or later you win the bad lottery. Go ahead.
Is that why you can have a benign tumor, like it's something that doesn't really affect your body that greatly?
Oh, benign tumor means. That's what a benign tumor means. All of us have benign tumors. We have a zillion of them. odds are pretty slim that extra cell growth would be a problem. That's the cancer that we worry about. Everybody got that? Game of odds? More radioactivity exposure raises the odds that you'll win the bad lottery? Yeah? Okay. Oh, 40, 3 Mile Island and Chernobyl. 3 Mile Island, we lost pressure. Chernobyl, we lost coolant. Either way, too much heat buildup. And I want to answer 41 and 42 kind of in parallel with the warm-up also. So in number 41, we have low-level, mid-level, and high-level radioactive waste. You have to know those terms. Low-level radioactive waste is basically no big deal. Sort of like hazardous material. You bury it carefully and you package it right and you can forget about it. Low-level radioactive waste is like when you go to the dentist and they put that like lead shield on you before they take an x-ray of your face or whatever. Don't know what I'm talking about? To protect the nads. That apron is kind of slightly radioactive. They just keep it hanging in the freaking dentist office. But when you get rid of it, you can't just throw it in the dump. You gotta like put it in a special box to bury it. Okay. Low-level radioactive waste is like the gloves that the plumber uses when he walks into this room, the little hair nets and like the little dust coats and like the little booty things. Y'all saw anytime I showed a picture of somebody working in a nuclear power plant, all those clothes, they're all low-level radioactive waste. You have low-level radioactive waste in your homes. The reason you're not supposed to dispose of electronics in the garbage is because these have low-level radioactive waste. And you know, if somebody's growing their carrots right next to it, that might be a slightly radioactive carrot, and you eat the radioactive carrot, and it just raises your chances of getting a bad lottery ticket. Yes, low-level waste? So you don't want to grow the carrots right next to the low-level radioactive waste, so you just put it in a special box and then you bury it. Low-level is not a big whoop. We're all surrounded by low-level radioactive waste. You don't have to freak out. Raises your odds, not a lot. Yeah. You're raising your hand or you're just sleeping on your wrist?
Yeah. Is cancer the only outcome from
It's probably the only one that matters. Because if I interrupt other chemistry in your body, usually cells have a way of checking in on each other. And everybody goes, oh my god, Heidi's falling asleep. We'll just chop her up and digest her and make our own cells. Your body has cell replacement. So if your cell has a failure that's not runaway growth, there's already a way to manage that. Your body like composts broken cells, so to speak. So most of the stuff that the chemistry breaks is not cancer and thus is irrelevant. You're already bathed in radioactivity from sunlight, and just because we're alive in our universe, and then from all your electronics, and like, oh, there's already done, well, you know, all sorts. And 99% of the time, it won't even make cancer, it just breaks. And when your cells break, it just make new ones. Mid-level radioactive waste is kind of sketchy. We've got to put it in really special storage. Mid-level waste, that's kind of gnarly. You have to bury it in like salt flats and like stuff that's not going to break for like, I don't know, 200,000 years. You got to bury it really deep underground, like a quarter mile underground or something. It's like pretty serious. But at least we've got a plan for that. We already have those special landfills. There's ways to handle it. What we're all freaked out about is the high-level radioactive waste. Like those fuel rods right there, that's a high-level radioactive waste. This stuff, high-level radioactive waste. I see a lot of falling asleep, but this is the one that you really got to worry about. High-level radioactive waste has to be managed full time. You got to keep an eye on it. Because what makes it high level is, the literally definition is very radioactive. Like, it gives off a lot of lottery tickets. It really raises your chances of a bad outcome. So high level radioactive waste is gnarly, and by the way, it's gnarly for hundreds of thousands of years / millions of years. It's going to continue that decay process for a long time. You don't have to read all this. I'm just going to try to see what I can remember from this. One thing you should know is, right now, the only plan we have is to hold on to it. Martin's nuclear power plant keeps piling up more nuclear waste in the backyard, and the only thing he can do is just keep an eye on it. There's no plan. We have a few places that are right next to power plants. And our Congress says the federal government is responsible for managing it, but we got no plans. So we just keep it in monitored storage, like what that guy's doing. He's monitoring storage. He wears a special safety badge. It's like a piece of plastic that he wears on his shirt. And as he walks through the storage facility, he's capturing radiation. When his badge changes color, he's done with that job for the year. He goes to clean toilets or work at the parking gate or whatever. Because he can only have so much exposure to his body before somebody else has to do that job. We literally are burning through people's radioactivity thresholds and keeping track of our trash. Yeah, bro?
What are some examples of like high level?
So I'm not really an expert. I know that high level includes spent fuel rods, fuel assemblies, I'm going to guess reactor core parts. Mid-level would be stuff that's been close that absorbs radioactivity. Maybe the plumber's tools, maybe like the primary cycle plumbing stuff. Low level I know is like super common. I worked with mid-level radioisotopes that were radio markers for DNA research. So I would turn DNA luminescent so I could take photographs of DNA prints. Have you all done the gel lab with a bio teacher here? Where you make that little thing and then you use the micropipetter to squirt stuff and the bars? That's a radioisotope. And if you work in a lab that does a lot of that, you got to wear one of those badges, and mine never changed color. My buddy Steve, he maxed out for the year. So we did have a plan for a while. We looked around the entire country and we thought, man, there's got to be some place we could bury all this stuff. Where would America least care about?
Hawaii or Alaska?
Where should we put our nastiest stuff without going on the ocean, which would be kind of sketchy?
Arizona.
It's got to be kind of central.
Mexico, Kansas.
New Mexico.
Oklahoma.
We landed on
Iowa.
Nevada.
Yeah, that makes sense.
What do you mind? Nevada. How could that possibly get any worse, right? There was like 1 or 2 decades. Like, all the congressmen were like, Nevada? Yeah, Nevada, Nevada. And then the congressmen from Nevada were like, wait, no, not Nevada, no. And everybody's like, yeah, Nevada. And Nevada's like, what? And the whole U.S. was like, yeah, Nevada. And people got uppity. Like, the governor's like, no, we're going to close all the roads. And like the feds were like, we'll bring out the National Guard, bro, if you want to do this. Like, we can do this. And I guess it got like super contentious. And meanwhile, there was like some nerd in Nevada who's like, wait, I know that spot. There's like an earthquake fault and groundwater and stuff. And the U.S. is like, okay, Nevada, you're stuck. And Nevada's like, no, we don't want it. And then eventually the nerd like got the right science, and he's like, see, earthquake fault, groundwater. So we built the whole thing. We got basically that far, and literally like shipments were starting to arrive, going through the processing, labeling phase before they got buried. And right before we put them into the ground, everybody's like, never mind, calling it off. And it's like, everybody tore it apart. So we built a place to put everything that we haven't put anything into. We're back to the drawing board, which is blank. We got no plan. So where does that leave us? Number 42, a classic College Board question. Why should we and why shouldn't we nuclear? What are some reasons that we should?
Super clean in theory.
It is super clean. Now,
Higher energy potential than other radio sources.
exceptionally concentrated, yes. And there's a thing that I'm not sure everyone will understand. Do you know what I mean when I say that nuclear energy is materials economic?
What do you?
Materials economic. You dig a little hole, use a little fossil fuel to move a little bit of content that creates a ton of energy. Because it's so concentrated, you don't need a lot of expenses to get the fuel to the place where you're going to do the stuff. You know what I mean by that? Materials economic, concentrated energy. What else? Clean, materials economic, yeah? That's right, no acid rain, no global warming, no CO2. Yeah?
I think 97% recyclable.
Uh-huh. Very little weight. I really like nuclear. And by the way, the safety thing is pretty doable. As long as there's no natural disasters, and everybody knows natural disasters never happen. You know, it is kind of a safe thing. And by the way, it's not like coal is any better. Coal makes more radioactivity than nuclear energy, because coal ash is radioactive, and you make a lot of coal ash. You know what I mean by that? We just bury that stuff in the ground, and that's radioactive. We don't give a crap. So total radioactivity, coal might be worse than nuclear. Go figure that one. So I'm kind of a big fan of nuclear, but I've got one problem. Yeah.
Well, if it was like mass marketing, would it be like relatively cheaper?
Nuclear is the cheapest energy to generate. It's the most expensive power plant to build. So if the government will help you put up the money up front, which costs the taxpayer money, then you've got like an eternity of cheap electricity, as long as nobody has to count for the waste disposal. Right now, there's no cost for waste disposal because we're not doing it, so it's super cheap. If you have to include waste disposal, it gets more expensive, and if you consider that waste disposal is for like eternity, that's a big cost forever. You know what I mean by that? And this is the part where I get really nervous. There's only one reason why we shouldn't do nuclear, in my opinion. People are worried about the radioactivity, I'm not. People are worried about the accidents, I'm not. The part that freaks me out is I don't believe a promise that lasts that long. If your 17-year-old boyfriend or girlfriend says they're going to love you forever, you should be skeptical. Because what do they mean by forever, actually? The best promise they've ever kept is what, a few months? Because they're 17, right? You know what I mean by that? I'm not trying to like whittle away at your young love, go for it. But you know what I mean, that there's like a certain credibility issue, right? Think about it. What does a society promise you when no language, no flag, no system of government, no national boundary has lasted more than a few thousand years? Our Constitution is 240 years old, and we're one of the oldest governments on earth. 240 years old. That's like a 17-year-old saying they're gonna love you forever. Like, bro, I just don't believe you. What are you talking about? You're like, what do you mean forever? Imagine 200,000 years from now, some nuclear waste leaks and kills a bunch of kids. Who's responsible? Who carries the legal responsibility that long? If we have a different government with a different language and a different currency, who do you hold accountable? Nobody. Eventually, over time, we've accepted that we're not going to be responsible for nuclear energy. Sure, I believe you that you're going to be responsible for this your whole life. But how do you pass that responsibility after you die? Because nuclear waste stays just as dangerous or even more dangerous over multiple generations. Who's in trouble? Like, who do you bust? Yeah.
Couldn't we just like send it to space or like?
Because rockets never blow up. Yeah, totally.
Well, like just make them, like, why would you just do that?
Because rockets never blow up. Totally.
So if you 1 out of 100 rockets would blow up.
That would be really bad. And more than 1 out of 100 rockets blow up. Yeah.
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 What if we just put it in the South Pole?
Well, that's actually not as crazy an idea as you might think, except the ocean is like a perfect circulator of all things. A deep hole in the ground might be better, and that's why we were looking at Nevada, but it's tough to make a hole deep enough, and you know the crazy thing, if you can make a hole in the crust, the radioactivity can get out. This is high level stuff. So it's super, super radioactive.
What if we just put it all in the hole at Chernobyl?
It's not that big of a hole. The wacky thing is, we that had nickel for everything. If we have enough spent fuel rods to cover a football field 12 feet deep with solid spent fuel right now. And that number's growing. That's just the US. That's just the US. A football field 12 feet deep. That's a lot of spent fuel.
Can't we just wait until
At that concentration, if it starts to melt down, imagine the amount of radioactivity. Consider that a nuclear warhead is like smaller than the Civic.
speculating?
And it's kind of like, floating through space and it's kind of